lecture is okay. Today's lecture is about functional equations on natural numbers, on naturals. That's right. So, well, I'm giving these four buffer problems. You can try these out. You can take a screenshot, or I think I should just share this Miro link in the chat so that you can see the problems. I'm seeing the link, guys. I've sent the link. You can view the whole board. So yeah, today's lecture is on functional equations on natural numbers. So these are the buffer problems. I will be discussing them uh, afterwards in the lecture. For now, I will be going through few interesting properties on natural number which we can exploit on functional equations. So this is gonna be our first problem to discuss. The problem says that we have a function from natural number to natural number which says that f of 2 is equal to 2 and f of m into n is equal to f of m into f of n for all m and n are naturals, and the third condition is simply that the functions are increasing. The function is increasing. So in here we can see one interesting fact that if I put m is equal to n is equal to 1 in second condition, I will get f of 1 is equal to f of 1 square. And since we are operating on natural numbers, I can say that f of 1 is not 0. So there's only one thing, f of 1 is 1. Now, the interesting thing comes here is how we proceed on getting other functions. If I have, let's say I have some, wait a second. I will be telling about you. I will be telling about induction to you in first part. So let's assume we know that f of n is equal to n, and it is true for all one less than equal to. I mean, wait a second. It is true for all n less than equal to some number k. We know that. So if I want f of n plus one, or uh, if I want f of n plus one, sorry, what am I writing? See, since we have got this, we can definitely say that f of n minus one is n minus one. And by the second condition, we can get f of n into n minus 1 is n into n minus 1. The interesting fact that comes here is that natural numbers have a increasing and decreasing step of 1. If I have a natural number n, then the next natural number will always be n plus 1. And the previous natural number will always be n minus 1 if n is not 1, of course. So this is the important thing that I will be using next. This is one property of natural number. Listen, we know from third condition that f of n is n, and f of n is less than f of n plus 1. And this happens for f of n plus 2 is also greater than f of n plus 1. This is 2. That is not set. That looks so like set. Yeah, 2. And this can go on till f of n into n minus 1. And the good thing is that we know what f of n into n minus 1 is. And that is n times n minus 1. The interesting thing that we can see that is since f of n is n, then f of n plus 1 is always something greater than or equal to n plus 1. F of n plus 2 is something greater than or equal to n plus 2. So on, where I get, wait a second, I have to move this a bit. Yeah, so here we have said f of n into n minus 1 minus 1. This is n, yeah, minus 1. Now we know that this thing is always less than equal to n times n minus 1 minus 1. Okay, now let's just focus on this thing. You can definitely see that here we can say f of n times n minus 1 minus 1 is less than n times n minus 1 and also greater than or equal to n times n minus 1 minus 1. Hence, these two are consecutive numbers, and we get that this thing is equal to n times n minus 1 and minus 1. And since we got this, we got equality in here. This is now no more an inequality. So what is this? This is no more an inequality. It is an equality. We can do this till back to n plus 1, and we can get that f of n plus I is equal to n plus I till I less than equal to what is this? Okay, wait a second. Sorry. Because of the above statement, we can say f of n is equal to n for all. Oh, shit. What am I doing? Yeah, sorry. F of k is k for all k less than n equal to n times n plus 1. And we can n minus 1, I mean. And we can induct this forever. So the only thing remain is where to start this induction. We have got f of 1 and f of 2. Now if we see that f of 4 is nothing but f of 2 whole square because of the second condition, which is equal to 4. And because of this, we know that f of 2 is less than f of 3 is less than f of 4, where f of 4 is 4 and f of 2 is 2. And because of this, the f of 3 is equal to 3. We have got a n and a n minus 1 to begin our induction. And by all of this, we can say f of set. That is not a nice f. We can say f of x is equal to x for all x belongs to natural number. If anyone wants to ask me something, they can ask anytime, even in between my explanation. If you don't understand, I will be coming up with three more variety of this same problem to give you ideas of more properties of natural numbers. Do anyone want to ask anything in this one, or
Um,
can I continue?
I have.
Yes, yes.
Can we do this without using induction at all? Actually,
You
we
can
can.
try.
I think myself. I have a different solution. It involves
Okay.
primes and all. We already know what F2 is, so that's the only even prime. And then let's say we know until like we induct, strong induct on like some prime which is like let's say P or something.
Can you repeat?
Like we use strong induction until some number P,
Okay.
prime. So then
Okay. Okay.
we know that like for every prime greater than P, it is always going to be like surrounded by two even numbers, which will be two times some number which is less than P. Because we keep changing our P for like every time we figure it out, then we can keep changing our P to the next P. So if we take like PK to be the to be the prime which have we have first used our strong induction on, then we can find out all the numbers until we get another prime, because all the numbers can always be represented as all composite numbers can be represented as the product of two numbers which are less than P, at least until we reach the next prime.
Yes.
So then we can, for the next prime, then it will be surrounded by two numbers that are both even. So there will be two times some number which is less than, which we already know what the value is equal to. So clearly we'll
Yeah.
get value will be whatever the numbers are. It will be like P minus one and P plus one. So then we can change our prime to the next to that prime. So then we can keep continuing this process until infinity. So we'll get that this will Pn will be equal to n for all n belonging to natural numbers.
Yeah. So what you're saying is correct. Well, I was willing to give the idea that natural numbers have a step of one, which is a really good advantage. So I took this method. You can always find a new method to solve new problems. So yeah, that was nice. Sorry. So yeah, let's continue. And this is a useful thing that I said, that natural numbers come in a step of one, because we cannot do this in real numbers. There's no next real after a real value, and that's a trade-off. So I will be putting next problem on the screen. Just a second. The next problem is another variety of this same problem. I actually have four variety of this problem, and which I will be doing the class, and two varieties I will be providing in problem set. Situated, complicated, copy, paste. Is the problem visible? Hello.
Yeah.
Okay. So in the second problem, the only thing changed is that now we have m and n to be co-prime. Is anyone having any idea what we can do in here? Any small idea? Well, so in this problem, we will be doing this same step which we did in here, the whole copy paste of this thing. Just Now it will be trickier for us to find f of 3 because of this condition where m and n are co-prime. We actually cannot find f of 4. F of 4 is, well, we cannot say f of 2 whole square because 2 and 2 are not uh, co-prime. So we are stuck in here. We did copy pasted the whole thing of this part, the induction thingy. Now all we need is uh, f of 3. So I took this problem too so that sometimes you do have to brute force even if you don't want to. Well, yeah, this is just one lame example of brute forcing. I hate brute forcing. So for f of 3, well, we does know that f of 3 is greater than 2. So that is all. We all we need to prove is f of 3 is less than 4. Right. So, well, the brute forces are not much motivating, but it can become the only option to proceed. So we need to prove f of threshold is less than 4. Now,
Um,
since we are, yes,
um, is this from BJV?
basic,
No,
well,
is it from BJV's book?
yeah, well, when I was first time doing functions and I found this book to be really interesting, so I thought to bring this book's content in the lecture
Yeah, it is. It is.
to share. So all of the problems that we are gonna discuss are from BJV actually. Even these four nice problems that I've given in here, these are also from BJV book. So I was saying that we do have to group for sometimes. And yeah, since we are working on the that we are working with the products in second condition where we have to do things with the number which are co-prime. We can see that 3 is a prime number. So the best thing, wait a second, f of 3 less than 4. I will be trying to motivate how to brute force here as much as I can. We we need to get this. We can already see this because of f of 2 is 2. Now, since we don't want to end up with really big numbers and we are working with co-primes, so the best option to do here is actually multiply f of 5 on the both side. Why I'm doing this will be clear in a few more steps. See, we can see 3 and 5 are co-prime, 2 and 5 are co-prime. All we have to do is prove that f of 15 is less than 2 times f of 10. Well, the interesting fact comes in here is that f of 10 is greater than f of 9. And why I'm saying this is, see, we know that f of 15 is less than f of 18 because of third condition, and f of 18 is 2 times 9. So it is 2 times f of 9, and f of 9 is less than f of 10. And we are done. So that was it for second problem. We brute force that f of 3 is less than 4 and greater than 2. So f of 3 is 3. Well, now I will be putting the third problem. Oh, and so the third variation of the same problem is to completely remove the third condition. The only idea in this thing is to tell you that when you have this multiplication thing, the first thing that you should look, or if you are not done with the problem, of course, you should look into primes. If you have these types of conditions. See, if I have some natural number n, I can always write it as p1 to the power alpha 1, p to the power alpha 2 till pk to the power alpha k. Uh, well, just a second, my device is almost discharged. I will be back in a minute. So I'm back. So the property of natural numbers which I want to tell you in this one is that we can always split a natural number in primes. And this becomes really useful when we have a condition which looks a lot like this. So all we have to do is f of n is f of p1 to the power alpha 1 and dot 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 not p, f of pk to the power alpha. Now, if you look closely, we can map any uh, prime to any other prime q. Oh, wait a second, any other. Just to give a clear picture, we can say that hmm, okay, wait a second. Yes, we feel this. Just to get a give a better picture, I can do this. 3, then it would be uh, 5 to the power alpha 3 dot 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 dot. And these alphas are any whole numbers. So in the end, we can get something that looks like this. Here for that. And to tell you why there will be infinitely many functions in here, we can just shift these parameters. Wait, I will show you. Like if I say P1 is 2, P2 is 3, and then Pn is nth prime, set. is in prime. And then I define another function which says that let's call it Gk of pi is just p of I plus k. Like I am shifting the primes. If I write that is if I write c2 of 2, then since p1 is 2, I will be writing p3, which will be 5. So just to tell you that there are infinitely many functions, I can just replace this thing and say f of pi is some gk of uh, pi. I can write it as 2 to the power alpha 1, 3 to the power alpha 2. Well, are you getting my point? Or I can just shift it. I just not the reason. I can just shift it. Hey, are you getting my point? I have a feeling that I'm not able to explain. I'm like lacking something to explain this. Hello, guys. Is anyone here?
Yeah.
Okay. So, are you getting my point?
Yeah.
Nice. So the basic idea was that if you find something related to multiplication and all in natural numbers, then you can always split the natural number in primes. That's very good part of natural numbers. And after that, let's move to the fourth one. So the interesting fact about the fourth problem is that now we are working on a function that goes from natural to a subset of real. You can see that in the problem. So the main thing I'm gonna tell you in here is that when you take the numbers or the conditions to a really big number, like sufficiently big number, then the conditions that you are working on starts in a funny way. Like maybe in a funny way that is helpful to you or maybe not, but many times it does. So we know that that is correct. We know that f of 1 is 1 because of the second condition.
We use fractions here, right?
What
We use fractions here, right?
fractions? Well, yeah, kind of like
In the
we
syllabus.
will be restricting few things and then we will be getting that it is then we will be bonding few things in a range and then proving that if it the take really big numbers then that range will be not satisfied and it will contradict the whole thing of our assumption. So we know this, and here if I look at any number which any function sorry any point in function which will be giving us a natural number is f of 2 to the power k. which is obviously 2 to the power k. So we have to work out to get we have to somehow work out and get numbers between 2 to the power k and 2 to the power k plus 1 obviously. So here I will let that you have some f of m which is equal to L. We don't know where L is. Okay. Now I can put some points on M that M is less than equal to, so M is greater than equal to 2 to the power k and less than 2 to the power k plus 1. Now see, due to the third condition, we can say that f of 2 to the power k, that is still 2 to the power k, is less than equal to f of m, that is L, n is less than 2 to the power k plus 1. So we have a range on m and L. How about dividing them? I can get 1 by 2 to the power k plus 1 is less than 1 by L is less than equal to 1 by 2 to the power k. So just multiply this equation and this equation. What we will get is a nice thing that we are able to bond m by L in a range. Oh yeah, one more thing. I am assuming that L is not equal to L. This is our assumption for now. So what I will be ending up with is this. Wait a second. Yeah, I will be ending up with this thing. Right? Yes. Yeah. So since we are seeing that M is not equal to L, then if we look closely, if this number goes too big, if I'm bringing this to the power, let's say n, the whole thing to the power n. To just visualize, if I say that this thing, the middle thing is just greater than 1, then if I put a really big power to the n, then I may end up with a number which, wait a second, I think I did something wrong. Just wait a second, guys. Oh, okay. Well, I really did a few things wrong. I had to look up at my own notes to figure out what I was doing wrong. So, wait a second, let me erase few things really quick. Sorry for that, guys. I'm assuming this for some m to the power n, we have this thing. For some m to the power n, we have this thing. And because of the which condition? Yeah, because of the second condition, I can write f of m to the power n is equal to L to the power n. Now, because of that thing, I can just write this, which is this, and L to the power n, 2 to the power k plus 1. Now just divide both of them. 1 divide 2, equation 1 divides equation 2, I mean. So we will be ending up with 1 by 2 less than m by n to the power n. Sorry, m by l to the power n, and this is less than 2. So yeah, now to give an idea, just imagine if m by l is greater than 1. If I raise it to a really big power, then it will definitely go beyond 2. And if the m by l is less than 1 and I raise it to a really big power, it will definitely get smaller than half. And to actually write it in a proof, well, there's a really cool approximation where if I have 1 plus x to the power n, it is just greater than 1 plus n. I will be using this now. Like you can prove this by binary, sorry, not binary, binomial expansion. I'm using this for now. If I assume that m is greater than n, then this thing will something look like 1 by, no, I don't need this part. This thing will look like this. From 1 plus, oh, wait a second. Why do I keep writing n in this place? This is L. Yeah. So it will be m minus L by L to the power n less than 2. And because of this approximation, I can get it to look like m minus L by L times n less than 1. Now, since n is any natural number, and in this condition we are limiting n, so this clearly contradicts the fact that this is true, because this is not true, it got contradicted. And the same thing will happen when I say m is less than L. We have to do the same thing with L by m. So that is, so, yeah, L by m to the power n. This is a less than 2. The same thing will happen here, and it will get contradicted. And lastly, we will get to see m is equal to L, and f of x is actually equal to x, yeah, for all x belonging to natural numbers. If anyone have any doubt, then they can ask, because after this I will be moving to 4 main problems of this session, which I have planned to discuss. If anyone want to ask, they can ask anything. Nothing, I guess. So let's continue to the 4 main problems that I have intended to discuss. Uh, let's take this problem. So now we will be going to discuss IMO 1977 P6. And this is a really interesting problem because in here I'm going to tell you one interesting fact, well, which is obvious, but it will be, but I will be using it to exploit and get my solution to the problem. And the property of natural number, one of the nice property of natural number is that if I take any subset of natural number, then there will be always one natural number d, which is minimum in this subset. We can always find a minimum point in natural number in a subset of natural number. Well, we cannot do this with integers and real numbers, but we can definitely do this in natural numbers, any subset. Well, you can see the problem. We have to find all functions which goes from natural number to natural number and satisfy this inequality. And we have to prove that it is f of n is equal to n for all natural numbers. So yeah, we can always find the minimum point. So the main idea is this, where I will be telling you, which I will be telling in this problem. And actually, there are two solutions to this. The second one is the inductive way, but the way we are inducting in the second solution, I will be willing to mention it because it is a good way to think. So yeah, let's assume that uh, D is the minimum of all f of n. Wait a second. All f of n that you can find minimum. Such that n is natural number, of course. D is the minimum. Okay. A simple question. If D is greater than or equal to 2, well, if we look at this condition, if D is greater than or equal to 2, I can, wait, yeah, I can always put a D, sorry, well, let's say f of alpha is D. So if I say, uh, what am I doing? If I write second condition as f of alpha is greater than f of alpha minus 1, um, wait a second, why did I wrote D in here? I'm assuming that m is greater than equal to, so not m, alpha. My bad, sorry. So alpha is greater than equal to 2, and if I write this, I know that this is D, and there's another f which is less than D. And I initially assumed that D is going to be the minimum. So this contradicts my assumption and leads me to the fact that alpha is 1. Okay, we got minimum as f of 1 is D, the minimum point. The next is the thing that I mentioned about subsets is because we are going to get in subsets. Here, wait a second, let me copy paste it. I will be using the same argument in another way. Control C, Control V. That's it. Okay. Now I'm not talking about the whole natural numbers. At this point, I will be talking about all of n excluding 1 because we have already found that in all natural numbers f of 1 is minimum. What would happen uh, if I say that we are trying to find out minimum where f of 1 is not included? The same argument will happen as the previous one, and we will end up that this time the minimum will be 2, where alpha is 2. F of 2 will be minimum. 2 will be minimum in this case. And this thing can go on. And by this, we can say f of 1 is less than f of 2 is less than f of 3 and so on. So we basically prove that the function is increasing always. And since we are talking about natural numbers, we know this is always greater than equal to 1. That would means f of 2 is greater than equal to 2, f of 3 is greater than equal to 3, and so on. So we concluded two things by the above argument of minimums is that f of x is actually greater than and equal to x, and the whole function is always increasing. Now, since we are trying to prove f of n is equal to n for all natural numbers, one of the logical argument comes is that what if we contradict f of x greater than equal to x plus 1? We can contradict, of course. Since we have found out that the whole function is always increasing, we can simply put these things inside the function f of x is greater than equal to f of x plus 1. Wait. Now, because of this argument, yeah, because we did this and we know that we are initially given that f of x plus 1 is greater than f of x. Let me set this. Yeah, and we were originally given uh, in the condition that this is this, then f of x is just nothing, which contradicts the whole thing. And boom, we are done with the solution. We get f of n is n for all natural numbers. So we use the property that there we can always find a minimum in a subset of a natural number. Do anyone want to ask anything? Or can I proceed? I guess I should proceed. This comes, uh, here comes the second problem. Well, I will be discussing the sixth one in the last because, to be honest, uh, it will be hard for me to motivate that problem. So I thought of doing that problem in the last. Now we will be going with the seventh problem. We can do it here. This is okay. So this is our next problem that we are gonna discuss. Is anyone having any ideas on this? Well, I initially intended to ask for ideas on this fifth one also, but sorry, I forgot. If anyone want to share any idea or anything, they can always say it between. Is anyone getting any idea what we can do in here? Anyone? I guess I should give like 5 minutes to even attempt the problem. You can attempt for 5 minutes. I will be back in 5 minutes. Then
Put n is equal to m is equal to n is equal to 0.
can you repeat? Can you repeat?
Can you put like m is equal to n is equal to 0?
Zero. Okay.
So
So
then we get f0 is 0.
yeah, we will get f0 is zero. I was writing. So any more ideas?
Then f of m square is equal to f of m whole to the power 2.
Yeah, very good. F of m. Well, these two will be coming in really useful things later. Any more thing? Well, the second condition is very important because if this don't exist, then our function will be f of 0. So f of x is equal to 0 for all x. It can be that function also.
So then we can write f of m squared plus n squared will be equal to f of m squared plus f of n squared. Like that.
Uh, Wait a second, can you repeat?
We can write f of m squared plus n squared in the input.
F of n square plus n square plus m square is equal to what?
F of m squared, where m squared is the input.
Well, can you repeat? Hello?
Yeah.
Can you repeat the whole thing? Because
No, this is correct. This is correct. What you have written
oh,
before.
it was correct. Okay. I
Yeah.
thought I wrote something correct. Okay.
No, this is equal to f of m squared plus f of n squared.
Yeah, so it is.
Yeah, that.
Okay. Well, any more cool ideas? Well, I will give you one hint. Well, this problem actually demands induction, and induction in a really cool way. I want you guys to focus what this thing can be more than what it looks.
Can we use like fixed points?
What?
Can we use like fixed points?
Fixed points. Well, if you find something interesting, then you can always tell. We may use fixed points.
Hmm. Okay, I'll do some work on it and I'll tell if I get the answer.
Okay. Well, what I want to tell you that the way you can induct is if we find some a square plus b square is equal to x square plus y square, then, well, if we know that what f of a is, what f of b is, what f of y is, then we can always tell what f of x is, because after like putting these in f and all, you see, and because of that, our problem would look something like this. This is how we can induct actually. This is like not a normal induction of one step. This will become a really cool induction in 5 steps, like in a step of five. We can get it to look something like this. Well, since I mentioned that if we know any three of these four, we can always find the fourth one. How can we use that? How to get actually this? Well, we can wait a second. Since we have zero, we can definitely put a zero in here. Like if I say b is zero, then a square is equal to x square plus y square. We can get Pythagorean triplets. The whole problem is visible now. Any ideas? Well, since I said in a step of five, well, that is a real good hint to think something like 5 square plus 0 square is equal to 4 square plus 3 square. Can you see something from which we can induct in here?
Can we use zero?
What?
We can't use zero, right? Because it's
No, we are working with n0, which are whole numbers,
oh okay, okay. Yeah, okay.
and not is whole numbers.
We can find out what F5 and F4 is. So then we can find out what F3 is.
Yes, you can.
So we'll get F5 will be 5, and then F4 will be 4 because we can write it as f of 2 squared, which will be f of 2 whole squared, which will be 4. So then we can get that F3 will be 3.
Well, sorry, my connection got lost for a minute. Can you repeat?
We'll get that F3 is 3 and F4 is 4.
Yeah. Well, well, one more thing. If I put m is equal to 1 in this condition, then we will get f of 1 is 1.
Yeah, and then you can get f of 2 is 2 and all that.
Yeah. And we can get f of 2 is 2, of course. And okay. So, well, I will tell now that the thing I was intending to say is that I've written it separately because these are five equations that you can like manipulate a bit and get, but it would take some time, which you can of course give in a really long exam of 3 hours or 4.5 hours. Well, wait a second, I will just write the whole equation. This is one of the five steps I'm talking about. The other ones are, well, wait a second. Yeah. So I was telling to concentrate on the five step I was saying because see, I used the zero square. We know one square and we know two square. So how about if we try to find 5k plus 1 this time? We know 5k because of these. Like I'm assuming that I know 4k and 3k. But again, this is whole square. What am I doing? Yeah, this is whole square. We know. I'm assuming that we know this and this because of we are going to adapt. We can find this. If I want to try to find this and assuming that I know f of 1 and 2 currently, I would try to do something like this to get a really cool equation that looks like this. Like it is just trying to manipulate your way through the equations. Can you guys see this? We can get 5k plus 1 like this. In another way, we can get 5k plus 2 by doing this. Uh, Sorry, my internet died again. Well, okay, it's okay. So the second one that we can get is this one. Mhm. Second, third, yeah. So what I'm trying to do is just manipulate my way through the equations 4k plus 1 whole square plus 3k plus 2 whole square. Then we can try to find 5k plus 3 to this plus 1 whole square is equal to 4k plus 3 square plus 3k plus 1 square 1 whole. And the last one is going to be this. So this is another way in which we can use induction in a really cool way. Like we are literally inducting on a bigger step, a step of 5. If I and in this induction I know 4k and 3k to find 5k. I definitely know 4k plus 2 and 3k minus 1 to get 5k plus 1 and so on for to get all 5k, 5k plus 1, 5k plus 2, 5k plus 3, 5k plus 4. And this will go on for all natural numbers, and finally we will end up with our f of x is equal to x for all x being natural. I mean, and not because that's our uh, range and domain. So the main idea of this question was how we can induct well on larger steps. And most important thing was that we can manipulate natural numbers in very different creative ways like this one. Well, the next problem that I'm gonna discuss is actually my favorite among all of these eight. Well, okay, and let's do.
Can I give an alternate solution to this problem which you actually said?
Yeah, definitely.
The fixed points thing.
Wait a second, which one?
The one which you just solved.
This one, the seventh
Yeah,
one, right?
yeah.
Okay, yeah, you can tell definitely.
So basically, like, if we consider like some set, like S, let's say, such that F will go from S to S, the codomain and domain will both be at S.
Wait a second. Can
Yeah.
you just repeat
Um,
everything?
yeah, we'll consider like some function. Sorry, we'll consider
Yes,
some set S.
some set S. Okay.
So then, like, then F will be like over S. We consider like that function over S, F over S.
From S to S. Using this.
uh, the, like then we'll get like if there's some element such that like there's some element, let's say E, which will belong to S.
Okay.
So then it will be a fixed point only if f of E will be E.
Yeah. Okay.
So that will mean that this function will be f of n will be equal to n.
Um, well, I didn't got what you're trying to say. So, well, it isn't. Who is this speaking actually?
Cautious.
Okay. So I'm giving you poems to write on this board. Yeah. Yeah. I think you can write now on the board. Are you on the board?
Yeah, but it'll be a little hard for me to write because I'm not on a laptop.
Oh, okay. Well, actually, I'm not getting your point. So, would
Um,
you like to repeat or something?
Maybe I'll write like a proper proof and then I'll DM you or something. Is that
Okay, that would be good.
okay?
So, let's get on to my favorite problem among all. Well, I will be giving you time to solve this one also. The problems on the screen. And the first thing I would like to say is try to guess what the answer will be. And just for a disclaimer that your intuitions for the answer will be really wrong. Well, I think that this is also an IMO PW. Let me check. That is IMO 1996 P3, I guess. IMO 1996 P3. So that is not a P. P3. So that's the problem. Guys, well, since we are running out of time and we have really less time left, the sixth problem in here, well, I will not be discussing this in class. I will be including this in my problem set, and also I will be giving some hint if you, I will give some hint if you want to. Like, I will just say this problem will need sorry, not induction. I will need to tell you what injectivity is, so I will tell for this problem 6. Well, you can continue to attempt this problem 8. Where was it? Yeah, here you go.
One thing we get that is f of n is equal to f of n.
If everyone here knows injectivity, you can just directly use the hint, right? You're on mute.
Thanks. Uh, so injectivity is just that f of a, if f of a is equal to f of b, then we can say, not, we cannot say it is always f a is equal to b. This is the literal meaning of injectivity. That's all about injectivity. So, well, actually, this problem I don't think is going to use injectivity. The sixth one is going to use injectivity.
Yeah, you were saying that something you're going to give right about the sixth one, so that's why I had said.
Yeah, well, I will be including the sixth one in my problem set. So, since we're running out of time, you know. Well, one interesting thing I would like to tell about this problem is that your first intuition will be that f of n is equal to n. Well, this is one of the solutions, not every single solution. This problem has infinitely many solutions, to be precise. That's what makes this a bit different than any other problem I've told you since the beginning of the lecture. Well, if anyone is not getting any idea, I think I should continue. Or if anyone is getting any idea to share, then they can just say it now, I guess. Does anyone want to say
Like
anything?
we are getting another thing that f of m plus f of n is equal to f of m plus f of n.
What is in f of, can you repeat?
F of m plus f of n
Yes.
is equal to f of m plus f of n. No, sir. Okay, no, that's f of m plus f of n.
F of, yeah, yeah, yeah. Well, I understood what you were saying. That is a H, not N. Yeah, still not N. Okay. So,
No, no, no. F of m plus f of n.
oh, here, okay, I see what you are saying. Let me erase it real quick. Well, let me check if it is true. Uh, how did you got this?
Like firstly, we
Okay.
put m is equal to n is equal to 0, then f of 0 is 0. From there we get.
Yeah, f of 0 is 0.
Then using that, we put m is equal to 0. Hence, f of n is equal to f of n.
Yeah, that is true. And we get this.
Now we take f on both sides of the above equation.
Okay. Then this becomes
From
okay.
there, after simplification, we get that f of f f of m
Oh,
plus f of n is equal to f of m plus f of n.
wait a second. Did you meant this? Am I right?
No, no, I
Guessing.
meant the previous one only.
Okay.
F of m plus f of n.
Wait a second. Well, it does not goes that way, I guess. You are saying to do put this in function, right? Like this
Yes.
in both side. So by that it would look that side will look f of m plus f of n the same it looks before. Sorry, this is n, and the right hand side will look f of m plus no, bro. It is just going to get this. You see, this will no. Wait a second. What am I writing? Sorry, sir. Erase this. Yeah, it will going to look like just one second. F of m in here plus f of n in here. It is going to look like this actually.
Shall I tell how I got it?
This one.
Yes.
Okay.
Take first we simplify the above expression f of m plus f of n is equal to f of m plus f of m plus f of n. We can write that f of m as single f of m.
Uh, you are going too fast. Like, can you slow down and say again?
Like from the initial expression given in the given as a condition in the question, we get that
Yes.
simplifying the RHS, we get that f of m plus f of n is equal to simplifying f of m from the from where I proved f of n is equal to f of n. That
Yeah.
side is equal to f of m plus f of n.
Yes. 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 This is f of m plus f of n. Well, is this visible because I'm just using white color on white? Let me see. That is visible on the stream, so I guess it would be good.
Now we
Yeah.
take f on both sides.
Okay.
That gives us that the f of
It will
that
give
gives
up the give up this. So give us this thing that I've written. Yeah, like f of n is equal to f of n. That means if I put a f in here, then the same thing will appear. This and this thing f of m plus f of n will get inside f, right?
no, like the LHS simplifies to f of m plus f of n. The right side simplifies to f of m plus f of n.
Well, that actually don't happens. If you look closely, are you
Like
getting?
like we if
Well,
we take
can you
like
check your work once again?
yes, like taking f of m plus f of n from the above condition, we can say that it's f of m 3 times f plus f of n.
Well, if you can, then can you write it on a notebook and show it on your camera, if possible? It would be better for me to understand what you are saying. So till then, I will continue. So let's separate this from our main set of equations. For now, I will be putting it in somewhere here. Yeah. So you can tell that again if you want to. Maitreya, if I'm pronouncing correct, you can tell that again. I'm continuing for now. So yeah, from this equation, we can see that f of n, say, f of n is a fixed point. Well, a fixed point means if I have some f of alpha is equal to alpha for a function, then alpha is a fixed point of f. That is the definition of fixed point. So yeah, f of n is a fixed point for all n, fixed point. Fixed. So the interesting fact in here is that well, for now, wait a second. Yeah, let's assume there's some another fixed point alpha like this. Let's assume there's another fixed point alpha. Now, if I put alpha in the above equation, then I can get one second. Yeah, I can get f of, if I put m is equal to n is equal to alpha, then I can get f of alpha plus f of alpha, which is also alpha. This is f of 2 alpha. This is the left hand side. The right hand side becomes, well, wait a second. I have to write this thing again. So it is actually f of m plus f of n is equal to f of m plus n. M, yeah, f of n. F of m plus f of n. Because of f of, because of this condition, f of m is f of m. So yeah, back to this, we are getting f of 2 alpha is equal to f of alpha plus f of alpha, which is alpha plus alpha, which is 2 alpha. And we saw that if alpha is a fixed point, then 2 alpha is also a fixed point. And next, if I put m is equal to 2 alpha and n is equal to alpha, then I will get 3 alpha as fixed point and so on. That means by induction and all, we can get k alpha is a fixed point for all k belongs to natural number. This is one good property of fixed point that I can see. If alpha is a fixed point, then all of its products are fixed point. Okay. Now we have seen that the products are fixed point. What about uh, any number between the products like alpha and 2 alpha, between 2 alpha and 3 alpha? And that will make us take some value beta, which is something alpha times, let's say, a. One sec. Yeah, alpha times a plus some remainder r, in which of course 0 is less than equal to r and less than alpha. After taking this, if I look closely, um, okay, yeah, no, just one second. Yeah, well, let's assume alpha is actually the smallest fixed point we have, the smallest one. Okay, well, if looks like a mess. Yeah, alpha is minimum fixed point. We are assuming this. Now we are going to do this. Well, for now, let's assume that beta is also a fixed point. Assume. I'm assuming beta is a fixed point. This means beta can be written as f of beta. And since I have a nice expanded form of beta, why not use it? We will get a alpha plus r. And since I want to mold it into this initial, no, not this, into this thing, I can write, since I know a alpha is also a fixed point, I can write it as f of a alpha plus r. Now we can use this condition and get f of a alpha, which is a alpha because a alpha is a fixed point, plus f of r. And since I initially assumed that beta is a fixed point, no, yeah, since I assumed beta is a fixed point, beta is equal to a alpha plus f of r, and a alpha plus r is actually beta. That means a alpha and a alpha will get sorry, a alpha and a alpha will get cancelled, and f of r is equal to r. That means r is also a fixed point, but there's one catch. I assume that r is less than 1, and the definition of alpha is that alpha is the minimum fixed pointer that I can get. But now I'm getting a smaller fixed point which is r, and that cannot happen. That means that me assuming that beta is also a fixed point, but wait a second. I did nothing wrong. R is not 0 in this place. Yeah. Me assuming that beta is also a fixed point is wrong. Beta is not a fixed point. Okay. Now this comes to a conclusion that if f of a alpha plus r appears, then it is definitely a alpha plus f of r. Now what? One interesting thing is about to happen in this situation. I am giving you 2 3 minutes to think anything that might be interesting happening in here.
I sent you in the chat why the reasoning for f of that thing which I was telling.
Oh, okay. Thanks. Let me have a look. Okay. So what you are writing? Well, I will just put up it on the screen. Control V. Hmm. We have this above this. Okay. We wrote it like this. Uh. Okay. This and this. Just one thing. Being given out the same way. Okay, yeah, interesting. That will be this and that will be this. Uh, Bro, look, let me switch to black for this one. Yeah, see, this thing that you wrote, you are writing it as this, right? This is where uh, you are getting it wrong. Well, if I let, okay, that is not that. Yeah, switch back to white. Okay, if I let, let's say k is equal to m plus f of n, then what this thing is saying is f of sorry f of k. Okay, and f of k is literally f of k. Set f of k, and f of k is f of m plus f of n. So that's what you are getting it wrong. See, you wrote it like this. Wait, yeah, you wrote it like this, but it is actually just m, not f of m. Can you see where you got it wrong?
Yes, yes.
Okay, nice that you clarified your doubt. I'm removing this from the screen for now. So where did I left? Yeah, I was on this part. We know that f of a alpha plus r is equal to a alpha plus f of r. Now the things will get really interesting. Really interesting. Well, since we are running out of time, well, we have ran out of time. I will just tell you that we can put anything as f of r. In fact, if I just write f of r is equal to some nr, we are taking this as any natural number. The not question, the initial condition will always satisfy. Okay. So yeah, that's what I was saying. Well, we can check it by putting what we found in here in this equation. Let's do this. Well, I would, let's say, what yeah, m is equal to a alpha plus small r, and n is equal to b alpha plus capital R. Then m plus f of n would look like a alpha plus small r. Well, wait a second. Well, since we have already ran out of time, I would just say that if you can put the whole thing in the equation and see for yourself. This just uh, like solving a linear equation. You will end up that LHS is equal to RHS if we have this. So yeah, actually, this is the final answer. In fact, we can write it in a really better and more beautiful way, where if I take this, this, yes, so the more beautiful way is this. Yes. No. One second. One important thing I forgot to mention. Since f of r is a fixed point, oh, wait a second. Oh, yes. Sorry, guys, I missed few things to tell you. We are not actually done. Okay, well, this is actually the original, the main thing that we are intending to find. There are few more things. Let's say I have two fixed points, x. Well, I'm speed running because we are already out of time. If we say there are two fixed points, x and y, these are fixed points. Then if I write f of x plus y, since y is also f of y, we can get f of x plus f of y, and hence this would look like something as f of x plus f of y, and finally x plus y. So yeah, if x and y are fixed points, then x plus y is a fixed point. Well, I'm actually doing this too so that all the fixed points are actually just multiple of alpha. There's no other fixed point. Okay. Oh, wait. Okay. Oh, sorry, guys. I already did that. What am I doing? This is stupid. Yeah. I have already proved that every fixed point is a product of alpha because see here I assumed this and it failed. So yeah, every fixed point is a product of alpha, and since f of r is also a fixed point, it has to be, sorry, not here. Yeah, this is not possible. So since f of r is also a fixed point, we have to write f of r is equal to nr times alpha, where nr can be any natural numbers. We have already proved that f of r is a fixed point because of this condition. This is looking like this. So yeah, this thing will become a alpha plus n r alpha. And yeah, look at this. We have a fixed point f of a alpha plus r is also divisible by alpha. You can say this a plus n r. And what is a? A is just a GIF of this number dividing by alpha. So in the end, we can generalize it as f of n is a product of alpha where we are adding GIF of n by alpha plus some another nr where this nr can be anything for all n belongs to real number. Yeah, well, nr are actually predefined. N0 is actually 0, notice, because we know f of 0 is 0. So N0 is actually 0 always. And from N1 to N alpha minus 1, We can literally put any natural number in there and predefine it, and like that we will get infinitely many functions. That's it. We are done with this problem too. Well, that's all of the problems I can throw on you guys. If anyone wants to ask anything about functional equation or functional equation on natural numbers, they can ask. I think I might as well stop sharing the screen.